Hi, my name's Nick Braun. I'm a quantum researcher at IBM, and welcome to Day 9 of the Qiskit Global Summer School. I'm here to talk to you about mitigating noise in quantum hardware, number 1. And what I'd like to convey today is the things I think about when I am trying to do my own research on actual devices. So let me take you through that, but first we'll start with a review. Olivia talked about the quantum hardware and how it works, but I'd like to review a few more things because it's very important for us to think about how this works when we consider how we can improve things. So if we look at an actual superconducting quantum hardware device, such as this 5-qubit quantum computer, we can take a close look and we notice we have a couple things going on here. One of those things is a superconducting qubit, which looks like this equal sign that's been rotated by 90 degrees. And that equal sign represents the capacitor pads of our superconducting qubit. Inside, we can find something special called a Josephson junction, which we know is a nonlinear inductor, and it's a small superconducting insulating superconducting interface. The other things are these squiggles, which are actually superconducting microwave resonators. These are just like the coax you have when you're cable TV at home, but they've been flattened onto the surface of a chip, where you have one signal pin in the middle, and you have the ground planes on the side of these. These are used for a few different things. For example, they're used to read out the states of the superconducting qubits. They're attached to the side of the chips where contact is made with the outside world. And in fact, what we actually do is we put in a pulse at the frequency of these microwave resonators, and we can observe the qubit state by the phase shift that is imparted on that pulse when we collapse the state into a classical 0 or 1. These things are also used as multi-qubit quantum buses. For example, you can see how they attach 2 qubits here so that we can entangle the qubits and realize the exponentially large Hilbert space that we use for quantum computation. They are also detuned from the qubits themselves. They are a different frequency, which helps them to suppress spontaneous emission, which causes the loss of quantum information from our qubits into the environment. Another thing about these things is that they are linear resonators. So they basically behave like an LC circuit. So depending on whether you learned LC circuitry from your circuits class, or you know what a harmonic oscillator is from your quantum mechanics class, basically what you have is a quadratic potential, which means the energy level spacing between each level is equally spaced. Which means if we wanted to encode our quantum information, say a 0 in the ground state and a 1 in the excited state, that wouldn't work in this case. And that's because if we try to drive between the 0 and the 1, we would drive from the 1 to the 2, the 2 to the 3, etc., because they're all the same energy. Instead, we encode the information in the qubit, which has a Josephson junction, and that nonlinearity makes this an anharmonic oscillator, in which case we can encode the 0 state as the ground state, the 1 as the excited state, and then because there's an appreciable difference between the frequencies between 0 and 1 and 1 and 2, we don't have to worry about leaking into the 2 state. We can address that. But actually that does impose fundamental limitations on what we can do that we need to be aware of, and we'll discuss later. And the other thing is that these the 0 to 1 transition frequency is around 5 gigahertz, which if you multiply by Planck's constant and divide by Boltzmann's constant, that corresponds to about 240 millikelvin, which means we need to be appreciably lower than that in temperature. Otherwise, we have a thermal broadening between our levels. And any thermal broadening of these states means there's an uncertainty or fluctuations in our frequency, which corresponds to a dephasing error, which we want to prevent in our quantum computer. So how do we actually do this? Our single qubit control is done by microwave pulses. And basically, our microwave pulses are, in this simplistic picture, a Gaussian envelope wrapping a carrier frequency corresponding to the 0-1 transition of our qubits. And we impinge this on our qubits through the readout resonator. And what these pulses actually do is they can rotate around any axis in the Bloch sphere in the xy plane. So for example, if we had a pulse that rotated you around the x-axis, say in this x90 pulse right here, Then if we shifted the phase of that signal by 90 degrees, we would be rotating around the y-axis, as in this picture. How do you get z? How do you get z rotations? Well, you can use a combination of x and y pulses to generate those, but really the only perfect quantum operation is the one that you don't actually do. So we implement these in software with something we call virtual z. That means the rotations come for free, and we just shift the phase of the subsequent pulses when we compile the actual circuits. And effectively what we see is, if we're not actually doing these pulses, the average single qubit error, as observed with randomized benchmarking from this paper by Dave Mackay, you can see that the average qubit error goes down. And so this is a trick that we play so that we can really highly calibrate single qubit pulses that consists of these virtual z's and these single qubit rotations around the Bloch sphere, such that any arbitrary single qubit gate can be written as this unitary matrix right here, this U3. And we actually decompose that in a way such that this U3 consists of, at most, z rotation, which is free, a square root of x rotation, another z rotation, which is free, another square root of x rotation, and another z rotation, which is free. So in this way, between any two qubit gates, between anything else going on, because you can realize an arbitrary rotation, you should see at most two square root of x pulses corresponding to the two 90-degree rotations you need to execute any arbitrary single qubit rotation. This is something I actually look for all the time, just to make sure that I've optimized everything accordingly. For 2 qubits, everything gets a little more complicated. So the 2 qubit gate, which we use, is typically C0, which we build out of a ZX rotation. By ZX rotation, I mean we take a Z polymatrix and we tensor product with an X polymatrix, and we get this larger matrix, which we call ZX. And then we use that matrix to generate rotations by putting it into the matrix that does the rotations, and we see that we have a rotation in the plus theta direction when the control qubit is in the 0 state, and a rotation in the minus theta direction when the control qubit is in the 1 state, given by this matrix right here. And basically we can think of that as the 2 separate cases, where we start with the control qubit in the 0 state and the target qubit in the 0 state, given in the purple, and if we apply the cross resonance, the target qubit will start moving to the right. Similarly, if we prepare the control qubit in the blue state in the 1 and the target in the blue in the 0, then if we apply the cross resonance, we see the target qubit rotate to the left. So in general, what we're doing when we entangle qubits is we're preparing the control qubit in the 0 plus 1 state, given by the yellow in the X, also known as the plus state. Then when we apply cross resonance, we're actually rotating the target in both the left and the right, as you can see, which is kind of impossible to depict on slides. But that's what's happening. But of course, this is kind of a simplistic picture, and we're going to care about the physics that goes on behind the scenes. So let's talk about that. One of the reasons we like the cross-resonance gate is it's an all-microwave entangling gate. There are no knobs, no flux tunes, no currents that you need to take in to control the qubits that can be extra sources of noise. So if we have a chip that we used to do a lot of gate research on back in the day, it looks like this, where we have one readout resonator to the left and one readout resonator to the right, and a quantum bus coupling the 2 qubits together. What I'm going to do right now is I'm going to Photoshop out that quantum bus and just talk about what would be the case if we just had 2 qubits that were not coupled to each other. So we'll talk about qubit 1, which will be the control qubit, and keep that in the red. We'll talk about qubit 2, which will be the target qubit, and we'll keep that in the blue. And if they were not talking to each other, they would be completely independent, and we would have something we call an energy level diagram. So basically, if both qubits were in the ground state, you would be in the 0, 0, given by the lowest part of this, and that would be the lowest energy. That you can't go any lower than the ground state. Then, if we were to excite, say, the control qubit, given by an energy omega 1, then we would have the state 1, 0, which represents just the control being in the excited state and the target being in the ground state. Likewise, if we excite the target qubit, given by omega 2, corresponding to Q2's frequency, then we would be in the 0, 1 state where we have the control in the ground state and the target in the excited state. Now these two are typically different given that the Josephson junction, which comprises the qubit, is going to be an amorphous material which in general has microscopic variations across the chip, which is actually a very good thing. And we actually need that for cross-resonance because we need to be able to address the qubits in frequency space. And so because these frequencies are different, we can do that, and that difference is given by this detuning, capital delta here. And in general, this is going to be something on the order of 50 or 100 megahertz, where our qubit frequencies are around 5 gigahertz. So a substantial fraction. Now, this is very important for fixed frequency transmodes and how cross-resonance works. And this also can be a limitation to how well we can achieve cross-resonance. But in general, what we're going to do next is we have a substantial frequency difference that we can address. We are going to actually couple these qubits together. So this doesn't actually happen. I just unphotoshopped the bus resonator. And this bus resonator couples the two qubits, and it gives a static coupling, which we call J. J is usually on the order of 2 or 3 megahertz, corresponding to a pretty small amount of delta. So J squared over 2 delta is relatively small. And this, because we've coupled them together, we've shifted the frequencies apart to the tune of J squared over 2 delta. And so this is like a hybridization of the qubits, but it's a very small hybridization. We call this the dispersive limit, in that the control qubit, an excitation in the control qubit, stays mostly like the control qubit, but picks up a small part of the target qubit to the tune of J over delta. And that's like something like 2 or 3 over 50 to 100 megahertz, so it's a pretty small fraction. And the the target qubit corresponds to something that mainly stays like the target qubit, but picks up a little bit of features of the control qubit. So in that way, we can kind of think of the control qubit as being the control qubit, the target qubit as being the target qubit, and we don't have to worry about these this hybridization so much in the dispersive limit. So one thing you might notice is there's actually a sign difference between these two, and that's really important for how the cross-resonance behaves. So if I want to control this system of 2 qubits, what I can do for single qubit rotations, like we mentioned on a previous slide, is I can do single qubit rotations at the frequency of Q1 for the control qubit. I can do single qubit rotations of the target qubit, Q2, at the target qubit frequency. But if I want to do 2 qubit interactions, then what I'm going to do is I'm going to drive the control qubit, but at the frequency of the target qubit. And this is why it's called cross-resonance, is you do the 2 qubit interaction, but at the opposite frequency of the target that you're actually applying the pulse to, omega 2 in this case. And that has the effect of, if your control qubit is in the 0 state, then you're driving Rabi oscillations around the orange, as you see here. And if the control is in the 1 state, then you're driving Rabi oscillations in the green, as you see here. So you're getting a state-dependent rotation of the target qubit because you're doing one of 2 of these, or both simultaneously, Rabi oscillations. So that is how it works in general. Now, what we're going to be concerned about actually is deviations from this kind of perfect ideal that we've presented here. But we'll see. It's not going to be that bad. So what we can do is we can actually measure the strength of this. We want to see and isolate the ZX rotation because we can build a C naught out of a ZX rotation of pi over 2. Those are equivalent up to single qubit gates. So we can do something we call Hamiltonian tomography, where we have this drive Hamiltonian we call the cross-resonance Hamiltonian. And what we see is we have actually a lot more terms than the ZX rotation I told you about. And that's true, but these are terms that come from the actual physics of the device, and these are terms that are not exactly desirable for our C naught, so they're terms that we have to deal with. And we have many different ways of dealing with them, with many different kinds of effects. So the first thing we actually do is measure them. And so this Hamiltonian tomography paper from Sarah Sheldon in 2016 kind of gives you an outline of what you do, where as you drive stronger, you tend to get a stronger or more ZX rotation as you drive stronger, but you'll get these other rotations as well. And so what I'm going to call some of these different rotations are the qubit terms. Because our superconducting qubits are actually transmons, We have terms that arise if we treated the cross-resonance in terms of qubits, which include this ZX interaction that we want, that we build C-naughts out of, but we also have extra shifts. We have a ZI, which is an uncontrolled rotation on the control qubit, corresponding to a Stark shift from the off-resonance drive of the control qubit. That's going to be something we need to control for, because that causes undesired Z rotations on our control, and it tends to actually be the largest term in our cross-resonance Hamiltonian. We also have an uncontrolled target rotation corresponding to IX, which is in phase with our cross-resonance interaction, so it's not that bad, but it over-rotates our target in a way such that we can't build a C-naught with that IX, so we have to deal with that. And I call these the qubit terms because they differ from the other interactions arising because our superconducting qubit is actually a transmon. So in addition to those, we have these kinds of crosstalk terms. So for example, we call IY our classical crosstalk. This term, while it's not all in IY, it could be corresponding to some terms in IX. The Y part causes problems because it does not commute with the IX or the ZX interactions that we desire. This could arise from microwaves leaking from applying the cross-resonance to our control qubit. They could leak to the target qubit and cause other rotations that are classical, but they are out of phase with the quantum nature of the things we want to do, which means they don't commute, which means it can cause all kinds of other problems. They cannot be canceled as easily. There's also a quantum crosstalk term we call ZZ, which is both driven by the cross-resonance and kind of an always-on feature of the static coupling we have between qubits. The ZZ corresponds to the fact that the sum of the energy levels is not exactly the sum of the target and control frequencies. So the 1-1 energy I showed you on the previous one is actually slightly off due to the higher order terms of the transmons, because there's interactions between those as well. So because that control target, both excited state, is slightly different than the sum of their terms, we have an intentional or an unintentional rotation of that's dependent on both of those being in the excited state. We call this ZZ. But we have ways to mitigate this as well. And I'll show you using Qiskit Pulse how we can do that later. So for example, from Sarah Sheldon's paper, there was presented one scheme for dealing with these kinds of things, and kind of maybe the most common way of doing this is doing something called echoed cross-resonance. So what we do in echoed cross-resonance is we apply half of the cross-resonance we need for the pi/2 rotation, the pi/2 ZX rotation, so this corresponds to something like a pi/4 rotation, to our control, which implements that entire cross-resonance Hamiltonian I showed on the previous slide. But then what we're going to do is flip the control qubit. And then we're going to apply the negative cross-resonance to that control qubit as well. This has the effect, because Z and X are both being flipped, the negative control and the negative cross-resonance multiply by each other, and you get an additive effect of both ZX pulses. So you can build that whole pi/2 rotation, but the Z and the IX get the opposite sign, because there's just one of them, and they get canceled. So if you were to then rotate the control back to its original state, then you would have exactly an RZX rotation. And if it was pi/2, then you add single qubit gates, and you get a C-naught gate. But of course, there's these other terms here. And so in this work, we actually applied a cancellation tone, which was basically a measurement of the IY term, and then we can apply microwaves at that same amplitude but out of phase to destructively interfere with it to get that IY term to go away. And so in that way, we get the ZI and the IX to go away through this echoing scheme, and we get the IY to go away through this cancellation tone. And this is one way that you can do this. I would say this is from 2016, so this is a little bit dated, and I'll show you some more modern ways that we're dealing with these undesired interactions. If you want to see what the effect of these interactions are, and the effect of the cancellation, you can ask the question of, well, if I did standard cross-resonance, what would be the path of my target qubit in the 0 and the 1 state, which is basically what the Hamiltonian tomography experiment is anyway. If we look at the control in 0 or the control in 1, we can trace the path of the target, and we see if we want to drive the target to the 1 state, we're going to go in this kind of very spurious path around the block sphere, which, as you might surmise, is not going to be the most efficient way of getting there, and you're going to encounter more error when you try to get to the 1 state because you're going all around and not going to the most direct way. However, when you add the active cancellation, you see that you're driving in more of a geodesic around the block sphere, and you're getting where you want to go in a more straightforward way. And so in this way, we can see we're going to accumulate less error because we're going in the shortest path possible, roughly speaking. This shows you why we need these why we kind of need these schemes, and we'll explore later the other kinds of schemes we use to do something effectively the same. Okay, so we talked about the ZX. ZX is one of the maximal entanglers, but there's a number of ways we can use the ZX, just as variations of kind of what we talked about on the previous slide. We talk about C knots. One of the ways that we build these C knots is from the echoed cross resonance, which exactly corresponds to the previous slide. We have this entangler. We build these RZXs, and we add some single qubit gates that then gets transpiled down to another single qubit pulse here, and that builds a C knot. So we call this the echoed cross resonance C knot. It is a C knot that is built from this echoed cross resonance pulse, and you can see that with this extra pulse here on the end. However, there's other work. However, I forgot to say that this pulse also comes in some variations, whereas this can be a Gaussian square or a Gaussian square drag pulse. The Gaussian square pulse is a square pulse, but it has a Gaussian rise-fall to it. And the Gaussian square drag not only has a rise-fall to it, but it also has the derivative of that rise-fall on the quadrature, which does things like prevent leakage or prevent leakage to other levels. It does things like prevent undesired terms from line dispersion, for example. There's reasons why we would want to add the drag pulse onto that Gaussian square. Another kind of cross resonance we do is a direct C knot. Here what we're doing is we're building a single cross resonance pulse, and we can use this at times because it generally is shorter because we don't have the echo pulses and we don't have the single qubit pulse afterwards. We're incorporating everything into the cross resonance pulse, where now not only are we having specific pulses here that are canceling the terms we don't want, such as the ZI and the IX, basically canceled by this light blue term, which is the target active cancellation. And we have the rotary type terms, which are done in the darker blue, which go positive and negative. We can calibrate those such that those cancellation terms also give us the rotations that we need to build a C knot out of the cross resonance. So it's kind of like everything all at once. And one thing you can't see on here is I told you the ZI or the Stark shift is the largest term. We can compensate those with a frame change, which is typically done either before or after this pulse is applied. So that requires a different kind of calibration strategy because we're not trying to zero out the effect of the crosstalk terms, but we're trying to tune them in such a way that they become useful to build a C knot. And you can read about this from my colleague Peter Yurshevich's paper on Achieving Quantum Volume 64 back a few years ago. Another thing that's even more recent is we can actually just deal with the echoed cross resonance on its own. This is not so common, but has been deployed and has been used in cases where we have very high coherence backends, and we can actually tune all of the entanglers to be the same length of time. And that opens us up to more error mitigation strategies. And when we're not limited to coherence, this kind of thing is allowed, but we want to deal with the entangling part of the pulse on its own. So we don't even add the single qubit gates to make the C knot, but we just give you the base entangler known as the ECR, or echoed cross resonance, as we were talking about before. So there are a little bit of variations. A lot of times you can't see this unless you ask the back end, which is things we're going to talk about doing today, what kind of C naught I have. Or sometimes you even need to look at the pulse schedule and see what is happening to, under the hood, what is happening with the physics to your qubits that is actually affecting the entangling operation that you want to do. Okay, so now that we're talking about pulses a lot, we're going to get into the pulse model. I'm going to show you kinds of the ways we think about things at a microwave pulse level. So I always like to start with the Bell state, which is created by doing a Hadamard, qubit 0, and a C naught between qubit 0 and 1. So this gives us the 0, 0 plus 1, 1 state. Now this is from the gate or circuit level model, but I want to see what's going on with the pulses under the hood. And we can do that using Qiskit Pulse. We can display what's called the pulse schedule of what's going on. And so we see a lot of things going on here. Let's isolate them a little bit. We can talk about everything in the blue as being a single qubit operation. These are done on the D channels or the drive channels. And so everything in blue is a single qubit rotation of sorts with a positive or negative amplitude, and light or dark depending on the real or imaginary, also known as the in-phase or quadrature components of that microwave pulse. The 2 qubit operations are done in yellow and are given on the control channels, which are given by U channels here, and you just see them at the bottom right here. But the same thing happens as you can have in-phase and quadrature parts of the pulse. And then in at least the static circuits kind of framework, we're going to do all of our qubit operations before we do a measurement. These measurements are given by the red pulses. These are much longer than the control pulses typically, and correspond to something on the order of a couple microseconds. And during these measurement pulses, because we're going to be pulling that measurement pulse that has a phase shift corresponding to the state the qubit collapsed in, we need to digitize that, so we have an acquire pulse telling the digitizer to start taking in data and multiplying that data by kernel and integrating that data and discriminating that data to measure a 0 or 1. But most of this talk we're going to be talking about the control pulses, although we do have some error associated with everything, so we'll talk about some measurement error mitigation. And maybe now is also a good time to talk about just a general feeling for where the errors lie in these operations. Single qubit operations have very high fidelity and are typically done with an error rate of better than or less than 0.1%. 2 qubit operations are typically quite a bit more expensive, an order of magnitude more error than the single qubit operations, but typically less, hopefully less than 1%. We can get those down in some of our best devices, 2.1%, for example. The measurement is now done with an extremely high fidelity, which has improved drastically over the years, and that's usually about to 1 or 2% error for a single measurement pulse. And that always amazes me because you think about how small these measurement pulses are, that you can extract that data from the qubit and be accurate to within 1% or so. Always amazes me. So now we know what these are. Let's talk about, we know what these are. Let's talk about what they're doing. So this is where a lot of the skill of the art comes in, because I can look at this and I can tell you exactly what these pulses are doing. So for example, these pulses, the single qubit pulses, are the drag pulses I mentioned earlier. This stands for derivative removal by adiabatic gate. And what this actually is we have these Gaussian-shaped envelopes of our carrier pulses. What we're doing is taking the derivative of that Gaussian and adding it to the quadrature. So you'll see that these kind of derivative ones where you have up and down are going to be oppositely colored from the larger Gaussian parts. And that's because they're 90 degrees out of phase to those. And these are used to prevent leakage and prevent line dispersion. And you can read all about it in this paper by Felix Matsoy from 2009. Another thing we do is these virtual Z's, like I mentioned earlier. The only perfect gate is the one that you don't do. But because it takes 0 time, we want to know when these are happening. So we represent these by these little arrows here, so we can see when a virtual Z or frame change is occurring. And you can read this from my colleague Dave Mackay from 2017. So another thing is this echo type pulse, which I told you that Sarah Sheldon did in 2016. You can see this occurring right here because you see the positive part of the cross resonance, an echo, which is this single qubit gate above it on the control D1, followed by the opposite amplitude of the echo pulse. And some more recent work by my colleague Nirja Sundararajan from 2020 was investigating using rotary echoes where you drive the target qubit while you're applying the cross resonance. And this can have the effect of reducing the IY and ZZ. So this can help us get rid of crosstalk. In kind of a more modern scheme, you'll see the rotary echoes employed to get rid of those terms instead of, not always, sometimes instead of the active cancellation. And you can read all about that here. So kind of being informed by this and knowing this are the things that we're going to approach. And this is kind of a review lecture. We'll go into this in deeper detail in section 2. The other things that we need to be concerned about are the other things Olivia and Zlatko talked about, such as relaxation and decoherence. So we consider relaxation as being kind of the more classical process where we have a piece of quantum information, we put it in the one state, and there's a bit flip from the one state to the zero state, completely due to spontaneous emission, just as an atom would spontaneously emit. However, there's a number of ways that that emission can be absorbed by the system. For example, you could have some defects near your qubit that are at the same frequency and that can absorb those can absorb that information, absorb that photon. So these are things we call two-level systems. They correspond to dielectric defects, perhaps absorbance on your system that are typically chemical and can cause relaxation from your qubits. The other kind of relaxation is caused by spontaneous emission, and this is due to the electromagnetic environment, something we call the Purcell effect, and that can be controlled and engineered, and is actually something I used to spend a lot of time doing. So there's always going to be some leakage, but there has to be a mode in which the qubit can decay into, and if you eliminate those modes, you can reduce the spontaneous emission. There are other superconducting phenomena that are inherent to the way superconductors work, such as quasiparticles, which are unpaired Cooper pairs, and vortices, which are little tornadoes of charge that thread a small amount of magnetic field that can impinge on type 2 superconductors. We don't need to worry too much about those. In some ways they can be engineered, they can be studied, they can be caused by radioactive effects such as radioactive decay in the walls or cosmic rays, and have been kind of an interesting area of study for the past few years. And vortices can typically be engineered away. The other kind of thing we have to worry about is the purely quantum errors, which are known as dephasing, which is when we put a qubit in a superposition of 0 and 1, that needs to be coherent in a way that there's a definite phase between those two states. And we call this dephasing because that's when there's an uncertainty in that phase. And that can be caused by a number of different things from the T1, such as fluctuations in the energy levels, such as the thermal broadening between states. If your qubits are hot, they don't have as well-defined frequency, which means there's going to be fluctuations in that frequency, and those fluctuations correspond to Z rotations. Those can also be caused by magnetic noise if you happen to have a tunable qubit, which we don't because we're talking about fixed frequency qubits. This kind of dephasing can also happen when you do a measurement, whether you're intentionally measuring your qubits or not. So if you have a residual thermal population in your resonator, those are going to be dephasing the qubit as well. Because you're collapsing the qubit into a classical state when you measure it, that eliminates the phase information between 0 and 1 because you can only get classical information out of the qubit. And then finally, what we kind of overall as a catch-all, we fold these two into an overall decoherence rate we call T2. And what that is a combination of both the relaxation and the dephasing. And this is actually what you measure in the lab. It's hard to isolate the pure dephasing in an experiment. You measure the T1 and T2 to extract the dephasing. And so that overall gives you kind of a feeling for how long your information stays quantum. So we've reviewed a lot of the physics, and I'm trying to tell you what's important about the way I think about how quantum operations happen. But just to summarize this and transition to what we want to talk about, which is running algorithms on actual quantum backends. We're going to switch from device metrics that we're talking about, such as the frequency of the qubits, which are very important to the ability of cross-resonance to be high fidelity. We have decoherence, which is the ability for the qubits to retain the quantum information in them, which is of course very important. The measurement fidelity, which is when you do a single shot measurement and you integrate that signal and you plot it on something called the IQ plane, which is the in-phase quadrature plane, same as we deal with the pulses. You can plot that on the complex plane and see what corresponds to a zero state in the blue and a excited state in the orange, and you can draw a line or do some sort of technique to classify those measurements as being a 0 or 1. But of course there's always some error. There's always an amount of quantum noise that comes along for the ride, but a lot of the noise from the amplifiers or thermal effects can cause noise to come into the systems as well. Likewise, our qubits are not actually qubits, but they're transmons, so there's a higher order level, the F or 2 level. This can be useful for things, but it can also be something that is leaked into, and so therefore it can act as kind of a speed limit to how fast we can do operations, because the Fourier transform of our pulses, for example, will have higher spectral content in this 2 level if we make the pulses shorter and hence the amplitude higher. So that serves as kind of a speed limit for how fast we can do things, meaning there's going to be decoherence that we're going to be affected by, and those two are kind of always competing against each other. That also affects the quickness in which we can do interactions between two qubits, but those are also affected by the coupling that we design between those, which is engineered so that there is a high fidelity operation between the two qubits and not so fast as to be uncontrollable. Now, these are the kind of device physics or device metrics that we're looking for, and what you might be thinking about as well. I don't really care about those. I am more interested in running things on hardware. For example, I really have this cool universal quantum simulation algorithm I want to run using phase estimation and the inverse quantum Fourier transform. Or maybe I want to do quantum teleportation and I want to send quantum information from one place to another. And what I want to show you is, in order to squeeze out the most out of the system, you're going to want to know what's going on, because a lot of the effects and a lot of the way we control things are areas of active research, and while we're always aiming to improve these fidelities and metrics, sometimes knowing the way that they are implemented is going to give you a key to how you lay out your algorithms or how you want to design your circuits, for example. So this all comes into something called the Qiskit transpiler. So now we're getting into the software side of things, and we're going to talk about how you actually run these circuits. So the Qiskit transpiler is basically where I work. This is kind of where the software meets the hardware of the qubits. This is where you can take the abstract system of something you actually want to do, quantum material-wise, very much along the lines of what John talked about in week 1, and you want to put this on a physical quantum circuit, which is something that we were just talking about that exists in our quantum computation center. So in order to transform this from an abstract circuit to a physical circuit, we call this the transpiler, because it's like a compiler, but because the input and output are both circuits, it's a transpiler. And each transformation the transpiler does, we refer to as a pass. And the pass manager inside of the transpiler is what combines these passes in kind of a linear order, but there can also be control flow, such as repeat this pass until it succeeds, or until it converges, or until the optimal cost function is not being reduced, for example. So we'll just talk about passes in general, because that's how I think about most of the error suppression techniques. So if you want to dig into this, there's some great resources we'll put in the description below, but basically it's operated on an abstraction of a quantum circuit called a directed acyclic graph, or DAG, which is how you think about circuits and act upon it. If you don't want to write your own passes, you don't need to worry about how the DAG works. We're not really going to talk about it in the rest of this lecture, but it's how I implement the ideas that I want to do. And I think the transpiler serves as a model for understanding and mitigating error for noisy quantum hardware. So I'm going to show you the kind of framework that I think about when I do these things. And so in general, basically what you're doing is you're thinking about this abstract circuit, say a quantum Fourier transform, but it could be anything. The physics of the device doesn't know what a quantum Fourier transform is. You need to convert it into something that corresponds to the Hamiltonians I've been talking about that we can calibrate and control. And so what you're actually doing is you're taking this kind of block circuit diagram and you're mapping it into something that the backend understands. In this case, it understands what arbitrary z rotations, square root of x pulses are, and c naughts. So this is a kind of representation. So for example, let's just go through some of the steps of this. This has actually been improved very recently in Qiskit because we now have a staged pass manager where we can address these individual parts by the stages they exist. And one of those stages, or the stages I will summarize here, are the ones I'm not going to go into later, but I can give you an example of what they do. For example, the initialization of the circuit means that any kind of larger type circuit, say that quantum Fourier transform consisting of 4 qubits, there's no 4-qubit operation on IBM backend, so we need to decompose that into arbitrary single and 2-qubit gates. And luckily, as we learned from theorists in the 90s, we can always do this. We can represent any kind of large qubit circuit in terms of single and 2-qubit gates, so we can always do this decomposition, although it can be classically expensive to actually do it. It can be done. So basically any qubit gate that is 3 or greater is going to be decomposed. So for example, the Tafali is a very popular gate because it first showed that you can have universal quantum computers. But it consisted of 3 gates where you have controls on Q0 and Q1, and you're doing the operation on the target, which is Q2. You can run this through the initialization stage, and by initialization I mean PM is the pass manager that I've constructed. And I'm just running it through the initialization, which is .init, and I run the circuit by doing .run on that circuit. And the output of that circuit is now something that is not ready to be run on hardware yet, but has been decomposed into the abstract single and 2-qubit gates you are probably familiar with. For example, we have Hadamards and T gates and C naughts in this case, but these are also not gates that are known. The C naughts are, but the Hadamard and T gates are not, but the C naughts are also going across qubits, which will need to be further decomposed with swap gates. So this is a simplification into single and 2-qubit gates, but it's only a part of that simplification, and it's not ready for prime time yet. It's nice to see the effect of each one of these stages because you can see how things are broken down in a very systematic way. So I'm a big fan of the staged pass manager. Translation is now we're going to take the native gates that the backend knows, and we're going to take these abstract gates that are not known by, say, the Hamiltonian that's been calibrated to do these things, and transform that. So this translation pass is interesting because you're going to basically send things that the backend knows how to do, and the backend can look it up and knows what microwave pulses correspond to those operations. The exception here being the pulse gates. If you were to add a pulse gate, then you are providing your own schedule and you're telling the backend the pulses it needs to apply to represent that gate. So in this way, you have this complementary system where everything needs to be decomposed into native or basis gates or pulse gates that have their own information and tell the backend how to run them. So for example, the T gate is unknown by the backend, but it's actually a pretty simple gate to do. We can do this with the pass manager .translation pass. We throw the quantum circuit in the run there, and we see that the T gate is actually just as we thought. It's a pi over 4 Z rotation, which is exactly what it is. This is actually free for the quantum backend. Likewise, we can do a swap gate. There is no native swap to the systems, but those can be translated to a series of 3 C naughts. And thinking about how this happens is very important for squeezing the most out of the quantum hardware. Now, some of the interesting things, like I mentioned before, is most of the backends are going to correspond to a C naught, but some backends that have been released use the echo cross resonance, which means they will need to be decomposed in a different way because the C naught is not a basis gate on those systems. The ECR gate is a basis gate, but they can be translated from one to the other, so it's not really difficult to go further to the echoed cross resonance. And then interestingly, future backends, if you'd like to read this work by my colleague George, he'll tell you about how you can build CZ gates using tunable couplers, which is some exciting work that we're going to be releasing in the future if you would be interested in carrying. Another interesting thing about these things is that now that we're in the era of noisy quantum operations, these Z gates, or corresponding to T gates, are free. They have 0% error. And the C naughts tend to be the expensive thing because they have an error around 0.5% or so. But in the world of error correction, C naughts are protected by error correction, but T gates are not. So you have a kind of a vice versa kind of thing where the T gates become expensive, in the near future, whereas they're 0% error right now. They're going to be not protected, so you have to distill them from magic states, which is a more complicated and resource-intensive thing when you have quantum error correction. Whereas your C naughts will have a much lower error rate because they're inherently protected by the quantum error correction codes. So that's something to look forward to as well. Another thing we can think about is the optimization. So I talked about how you can do an arbitrary single qubit rotation with one of these U3 gates, which means you only need a maximum of 2 square root of x pulses in total between entanglers. So there's some things you can do. So if I have the series of different gates on a single qubit, I can run this through the optimization pass of the staged pass manager by doing pm.optimization.run on the quantum circuit. And I see that all these things get combined into actually a single square root of x pulse and an RZ. So this effectively long series of gates has been turned into a single microwave pulse and a Z rotation that happens in software. Similarly, we can have optimization of 2-qubit gates because a C naught is its own inverse. So if I was to throw this circuit on the left here through the optimization routine, I would see that these two C naughts on the end cancel each other and go away, and likewise my Hadamard gate has been decomposed into RZs and square root of x's. And then finally, usually the last stage of transpilation is the scheduling, where you need to actually physically time the circuits and put the pulse information in and the timing so that the backend knows when to play these actual pulses. And so that can have some interesting effects as well. So I'm just going to do this kind of entangled gates. I'm basically building these out of controlled Zs, which are now represented by C naughts and X gates. Or maybe I did something else. I don't know what I did. But anyway, I have this circuit. And I can schedule it in a couple different ways. For example, I can do as late as possible scheduling, which means I push the gates later in time as far as I can. And you can see the effect of this with a visualization tool we call the timeline drawer that you can import from Qiskit.visualization. This will show you the time of the operation on the qubits. And you can see the 2-qubit ones have a very long time. This corresponds to actually the fact that J over delta is very small, as mentioned on earlier slides. Single qubit operations are very short, usually 35 nanoseconds or something. What you'll see here is those X gates now have been pushed all the way to the right, corresponding to later in time on the X-axis, to as late as they can be done because they need to be done before the entangling gate. Likewise, the X's on the other side have been pushed later in time as to the very end of it because that is the latest that they need to be done. They need to be done before the C naughts, but they can be done as late as possible. Likewise, we can do as soon as possible, which means those initial X gates are now done initially at time 0, as soon as they can be done. And the times that were at the end before have now been moved to the left, as close to the C naughts as possible. So this is as soon as possible timing, which is usually not the default. We usually go with as late as possible timing because it allows the qubits to remain in the ground state for as long as they can be idle, which means they don't incur error from relaxation. So typically the default is to do the ALAP scheduling, but this is a piece of freedom that you have, and as circuits get more complicated, there are more timing schemes that you may want to consider. Speaking of errors, there's a number of ways that you can get error data out of the IBM backends. First of all, you can go to the IBM Quantum Services site at quantum-computing.ibm.com. And we're going to be talking about, in this series and the next, IBM Q Kolkata. You can look up in a graphical, visual way and see what the device metrics are that we've been talking about. These are all kind of available. You can have a scroll-down menu that tells you the T1 of this case. T1 of whatever qubit we're looking at is 130 microseconds. You can look at the C0 error corresponding to the bars between the qubits, and you see the layout or the topology of the qubits, which is also important for executing algorithms on real backends. But as you kind of look at these and you play with these graphical utilities, you realize this is good for a handful of qubits. If you're just doing a small system, this is sufficient. But as you scale up, we're going to need to do this a little bit more algorithmically. So we're going to need to get the numbers, and we're going to need to operate on those numbers, and we're going to need to do things that can run algorithms, classical algorithms that can analyze those numbers and come up with optimal solutions for us. And that's a lot of what I want to tell you about today, is we can do a lot of this in a very systematic way. For example, if I want to know the kinds of device metrics of these, I can get this from the backend. So from backend.properties, I can say get the T1 of qubit 12. And I get it out in SI units, so this is in seconds. And I see that qubit 12 has a 183 microsecond T1. So that's cool. I can feed that into a program later, and it can do something, say compare that T1 to other qubits to see whether I should use that one or the other one. I can look at the gate error, for example, in a systematic way. I can say, what is the C0 error between qubits 0 and 1? And we have here that it's 0.46%. That's a pretty good one. So I should keep that one and maybe use that C0 over another C0, for example. I can look at the readout error. This maybe in a static circuit type of sense doesn't matter so much because I can always do more shots or average more. But it will matter a lot when you're doing, say, dynamic circuits. We can see qubit 12, for example, has a readout error of 1.2%. There's other general properties that we can add to the system to give you more device information that can be actually very useful if you know what you're looking for, and this can also vary and depend on what kind of algorithms you're trying to run, which we'll talk about earlier. But let me just tell you what this kind of general information means here. So basically this JQ here, this is the J I talked about with the device. This is inherently due to the coupler, which couples the qubits and allows us to do cross-resonance. This is the J coupling between qubits 12 and qubits 13. And I can see this in the units of gigahertz, and it corresponds to something like 1.9 megahertz. So close to the 2 or 3 megahertz I told you earlier. It's a little bit lower. We can also measure the ZZ, which is the static ZZ, which is the always-on quantum crosstalk error between qubits 12 and 13. And we can see that in units of gigahertz. And we can see it's about minus 42 kilohertz, which is, generally I would say not bad, but if you're doing quantum volume experiment, you might want to be concerned about that because they tend to be susceptible to ZZ errors. We can also look at the backend configuration. We can get the coupling map on the left in an array of pairs that are coupled together on the right. And that allows us to analyze things and realize which qubits are next to each other and realize how we need to lay out our circuits. We can do graph theory optimization or something on that to figure out the best qubits to use or the most efficient ones to use, for example. And then any of that pulse information I showed you on previous slides, you have access to as well. And you can get that from backend.defaults.instruction schedule map. It has all of the pulses that are calibrated, tuned up, and you can look at them and you can manipulate them and you can see what they look like and analyze them to your heart's content by getting them from the instruction schedule map. And just as an overview to conclude this first part, I'd like to show you the way I think about things and the way we can install any extra things other than Qiskit that we might need to do. But overall, I'd like to think about this in kind of 3 different ways. So the first problem I think about is qubit mapping, which is to be smart about the qubits that you're using. And you can do this in a very systematic way, which I will show you in the next lecture. I tend to divide this process into 2 things. which is routing and layout. And routing means moving your circuit to an arbitrary topology where I have to insert swaps in order to move quantum information due to the lack of all-to-all connectivity of our planar superconducting quantum systems. And then layout, which is picking the best physical qubits that are compatible with such a topology. I like to break it up into two different ways at least. The next one is error suppression, which I like to think about as using physics to reduce errors. So in this way, we can think about ways we can parallelize the operations in our quantum circuit without incurring additional error. So that will also depend on the algorithm. We can think about things like pulse scaling, which are things that I started doing a few years ago for my own research, which correspond to just using the amount of cross-resonance you need to do a given rotation. We also have dynamical decoupling, polytwirling, which will randomize the errors on your qubits experience. There's measurement error mitigation, so that will be one of the measurement techniques we will talk about in the next lecture. And there's always going to be more that we put in. But basically, I think about that as using the physics of the system to reduce the errors. And then there's finally error mitigation, which is kind of a more elaborate technique where you analyze the circuit in certain ways. This kind of corresponds to zero noise extrapolation, where we can controllably add an amount of error into our circuit. And by doing that in a controllable way, we can try to extrapolate to the case where there's no noise, if we understand our noise well enough, and probabilistic error cancellation, in which we can actually try to learn the noise by twirling over the error channels, and then apply the inverse of that noise channel in the best way possible to achieve a better expectation value. Now, in some ways, I think of these first two as being just artifacts of transpilation. You're just taking a circuit to a smarter circuit. That's all there is, and you're running it with no additional cost, or maybe a minimal overhead and cost for the measurement error mitigation, for example. The error mitigation, however, means that you need to transpile your circuits differently, such as you're controlling the error in a way that you can analyze and you can model, and that you can try to predict what the actual results in the case of zero noise would be. So this requires an overhead in the amount of quantum circuits that you need to run. So I think that's very important between the techniques on the left, which are basically free in terms of quantum resources, and the technique on the right, which are not as free because you need to run more and more circuits. And these places also live in the techniques in which do these kind of live in different techniques, for example. And that's because Qiskit is a hardware agnostic platform. It will run on any kind of gate-based quantum backend. So a lot of this error suppression and error mitigation techniques are very particular to superconducting qubits, as I've detailed the physics of or reviewed the physics of before. So you need to know a lot about how the system actually works in order to apply these techniques, which is why they don't belong in Qiskit and they belong in these other Qiskit related repositories. So Qiskit Partners is one of the ones that does some layout routines, including measurement error mitigation. Qiskit Research is another repository that makes it easier to do a lot of these error suppression techniques by basically taking the pulse level information that's involved in it and putting that into the software in this kind of very hardware unagnostic platform. The Qiskit IBM runtime also does this, but this IBM runtime does this kind of under the hood in a way where it's not always apparent what is happening, and that's done for its own reasons, such as the ability to abstract these mitigation routines away for people that don't really care about them. And for example, the heavier resource-intensive techniques, such as zero noise extrapolation and probabilistic error cancellation, are going to be done in Qiskit IBM runtime. Now, a plug here. Let's talk about the error suppression techniques I reviewed in quite some detail in the Nick Knows Volume 2 series, or Season 2 of Nick Knows. And at some point, probably at the same time this comes out, the Coding with Qiskit runtime will come out, where I detail zero noise extrapolation and probabilistic error cancellation with Qiskit runtime. But in the meantime, if you want to get ready for the next hour or so before the next lecture, we can talk about installing these things. This is relatively straightforward. Most of these are pip installable. For example, from Qiskit Partners, you don't need to know where this repo is. You can just type in pip install mapomatic at the command line or Anaconda prompt, and this will install some layout tools that we're going to talk about. There's a measurement error mitigation technique that is used, that we used, although it's not the one used by runtime, called matrix-free measurement error mitigation, which is also pip installable by pip install m3, written out. Qiskit Research, the topics of the Nick Knows Season 2 episodes can be installed by cloning the repository on github.com/qiskit-research/qiskit.research, moving into that directory and installing an editable local copy within your environment, and that will give you access to the parallelization, pulse scaling, dynamical decoupling, and polytwirling. That's mainly what goes on in there. And then, of course, Qiskit IBM Runtime, you can do pip install Qiskit IBM Runtime. This will give you a different flavor of measurement error mitigation called twirled readout error extinction. It will give you access to zero noise extrapolation and probabilistic error cancellation. And these are enacted through the resiliency levels that you can invoke in the estimator, for example. And that's all we have for this session. I'll see you very soon, where we'll go into detail in the Qiskit code that can actually implement these physics ideas we've talked about. I've been your host, Nick Braun. Thanks for watching.